All right, guys, so here is what we're going to do. We're going to look at limits, but we're going to look at for, I would say, like an algebraic approach. So how do you find the limits algebraically? Because essentially that's some of it you'll have to do. Basically, a question would just be like, find the limit of blah, 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 and you don't have a graph, and you can't use your graphing calculator because there's a section of it where you can't. So you need to be able to think through these. So this comes into two parts. So we'll do part one now. And so let's look at that. So consider the function 1/2 times the absolute value of negative 2x plus 4 and then minus 4. And so the graph is shown right here. And so we are going to look at this, and we're going to find the limit using the equation. So basically, we're just going to find the limit as x approaches a. To using the equation, basically, we're going to use what's called substitution. We're just going to find f of a because we can look at that on the graph. So, if we have on this first example here, we have the limit as x approaches 0 of f of x. So what I'll have is basically f of 0. So that would be 1/2 times the absolute value of negative 2 times 0, and then plus 4 minus 4, okay? And so then simplifying that down, we would get negative 2. Now let's look at the graph as x approaches 0, which is right here. So as it approaches 0, as my x approaches 0, what happens to my y? Well, my y's are getting closer and closer to this value, which is 2. Excuse me, negative 2. So you can see how substitution obviously works there. So let's look at the next one. So as x approaches 2 from the right. So we're still just going to use 2 here. So we're going to find f of 2. So it'd be 1/2 times the absolute value of negative 2 times 2 plus 4 and then minus 4. And so then we would get a negative 4, simplifying that down. And so therefore as, let's see here, let's erase all this so that way we can look at this. Now we're going to find the limit as x approaches 2 from the right. As x approaches 2 from the right here. What's happening to my y values? When my y values are approaching right here, which is negative 4. And then same thing as x approaches 10, but we can't really see that on the graph, but we can fill it in. So basically, remember, that's just going to be like f of 10, which is 1/2 times the absolute value of negative 2 times 10 plus 4, and then minus 4, which is going to be a positive 4. And then if we were to carry this out here, it would cross here at 4. If we looked at the graph there, works out both ways. So when a function is defined and continuous over x equals a, so it has to be defined. So like if we have, if we're approaching as x approaches 0 and x is in the denominator, to make the denominator 0, it's not going to be defined there. So have to do some manipulation. We're going to look at that later. How can we find the limit as x approaches a? How can it be found analytically? Well, basically, since they told us that f of x is continuous, which, remember, continuous means that you don't ever pick up your pencil, okay? Then the limit as x approaches a of f of x is equal to f of a. So whatever this number is here has to be the same, okay? So I'm just going to plug that number in to f of a and figure out whatever that is. So that's going to be that limit. So we're going to look at that, what this looks like, just kind of do some practice in here. All right, so we have the limit as x approaches 3. So what I'm going to do is I'm going to replace x with 3. So I have 1/2 times 3 squared minus 2 times 3, and then plus 3. And so then I'm going to, this becomes 4.5 minus 6 plus 3, which is 1.5 or 3/2. Probably, I mean, either one. Obviously, again, we kind of talked about this, but you don't have to simplify on a free response question. But if it's multiple choice on the AP test, you do have to simplify. So you would want to write either one of those. So let's look at this one here. We're going to replace x with 3. So this is going to be equal to 5 times 3 plus 2 divided by 2 times 3 minus 3. So that's 17 over 3. And that's just it. Just leave that there. It doesn't become a nice, pretty decimal, so just go ahead and leave it as a fraction. Let's look at this example C here. Even though we are approaching 2 from the left, we're still going to replace x with 2. So let's plug those in. So I have the square root of 2 plus 2 minus 1 divided by 2 plus 1. So this is going to become 2. So I have 2 minus 1, which is 1, divided by 2 plus 1, which is 3. So it'd be 1/3. All right, so now we're going to, we have a sign here. So the limit as theta approaches pi over 2 of sine times 2 theta. So that's going to, remember, we're just going to replace theta with pi over 2. So this is going to be the sine of 2 times pi over 2, which this just becomes pi. So add the sine of pi. So this is basically the sine of pi, which is 0. So pretty easy right there, huh? You're going to have to be able to remember the unit circle. That's just going to be kind of big here. And it's not going to stop here at limits. It's not like, hey, I can remember the unit circle for now, but now I can forget it later on. You just got to remember it all the time. So just we'll do lots of practice on that. All right, so I'm going to replace theta with 2 pi over 3 because as theta approaches 2 pi over 3 of cosine theta over theta. So this is going to be the cosine of 2 pi over 3 divided by 2 pi over 3. And so the cosine of 2 pi over 3 is equal to negative 1/2. And then we're going to have 2 pi over 3 still. And remember, when you divide a fraction, you're going to flip and multiply. So this is like multiplying by 3 over 2 pi. So that goes there. Then I'm going to have negative 3 over 4 pi. And that is your solution. There you go. So then the next example, which we have a log. So as x approaches 9 of log base 8 of 11 minus x. So again, just replacing x with that value. So I have the log base 8 of 11 minus 9, which is the log base 8 of 2, which is 1/3. So just replacing that value there. All right. So what does happen if if you have something that is an undefined value? So we kind of talked about this, but when the denominator is going to end up being 0, it's going to be undefined at that point. So how do we find the limit of that? Because that can happen. We've seen that happen, right? We've seen it not be defined. So, and then still find the limit. So the limit as x approaches negative 3. Let's see here. if we try to put the negative 3 here, so I'm going to end up with negative 3 squared plus 4 times negative 3 plus 3. And then all over negative 3 squared plus 2 times negative 3, and then minus 3, then you're going to get 0 over 0, which is undefined. You can't divide by 0. So then do you just have an undefined limit? They're still going to approach some number unless it just doesn't exist, which would mean that there's a jump. But that still doesn't necessarily work out as far as undefined, because remember, we've been able to find the limit of something that was undefined, but is just approaching a different number. So we shouldn't be we just want to kind of be aware of that. So then again, if we plug in 1 here, I'm just going to do it with one of those. So I'm going to have 1 squared plus 4 times 1 plus 3. About 1 squared plus 2 times 1, and then minus 3. This is 8 divided by 0, which is undefined as well. Remember, you can't divide by 0. Even whenever it's 0 divided by 0, you still can't divide that. So, these two go together, so it's still undefined at that point. So just because a function is undefined does not mean that it doesn't have a limit there. Remember, we talked about whenever there's not a limit, remember, if it is going to miss on the high five. So that's whenever it doesn't have a limit. So let's look at the graph over here. So we looked at one similar to this almost at the very beginning. So as the limit as x approaches negative 3, if we look at this on the graph, it's going to approach, which I read this up here, positive 1/2. As x approaches 1 from the left, it's going to approach negative infinity. And as it approaches 1 from the right, then it's going to approach positive infinity. Now, obviously, the limit does not exist at 1, obviously, as you saw that up there, but because they miss, okay? All right, so what we'll do algebraically or analytically, that's those two I would say is kind of interchangeable. I will say more algebraically. That's just how my brain works. So we will perform some algebraic analysis to find the limit of the removable point discontinuity. So we'll do the cancellation process. So what we're going to do here is we are going to factor. So that's one of the ways that you can do this. So if I were to factor the both top and the bottom, so this would be the limit as x approaches negative 3. And so the top one, we're going to have x plus 3 times x plus 1. And then this is going to be divided by x plus 3 times x minus 1. And so you can see that x plus 3 is a common factor in both of those. And so that's why you have a discontinuity. Then you could plug in from here, you could replace. So this would be negative 3 plus 1 divided by negative 3 minus 1, which is going to be negative 2 over negative 4, which is a positive 1/2. That's why the limit we just looked at on the graph is 1/2 from that factoring piece. All right, so based on our knowledge from pre-cal, we know that if a rational function has a non-removable infinite discontinuity, graphically, a vertical asymptote exists. Since the y values do not approach one specific value from both sides at a vertical asymptote, then the limit does not exist. However, we can determine if one side one-sided limits approach negative infinity or positive infinity. In order to do this analytically, we will marry the numerical, graphical, and algebraic approaches for each limit below. Determine the sign of the simplified function at the value of the right or to the left of x equals 1. So basically what we're going to do, so remember we factored this to be, let's see, x plus 1 times x plus 1. X plus 3 times x plus 1. So remember, we factored that. These two divided out. Don't say cancel. I might have said canceled earlier. Apologize for that. So then the simplified form. So then we're going to pick a value to the left of, on the number line. Think about that. Left of 1, so 0.9. And if we get a positive divided by a negative, then this is going to approach negative infinity. It's going to be negative infinity. Okay, so for the simplified form, pick a value to the left. It's going to approach negative infinity. And then when we pick a value to the right, so just a slightly bigger than 0.1, slightly bigger than 1, if you get a positive over a positive, then this is going to be positive infinity. So anytime if you have a negative anywhere, it's going to be a negative infinity. If you have both positives, it's going to be positive infinity. If you have both negatives, it'd be positive infinity as well. All right, so that's it for just the first part. Okay, so we talked about substitution and we also talked about cancellation. So if you can make sure that if you can't find that by substitution, the next step is going to be try to factor out either the numerator or the denominator, or maybe even both of those. Probably both of them. There's a couple of them I don't think you have to do both of them, and I kind of gave you a hint because there's a perfect difference of squares. So you want to pay, because I forget about difference of squares, so I'm just trying to give you a hint to look for that. That's what you'll have for your practice, is that just that substitution, but also look for some where you have to factor the top and the bottom, and then divide out those common factors and then substitute in. And that's it for the first part. We still have some more, but the first part of finding these limits analytically.